Welcome to DCL 092. This is part two of a three-part series introducing basic concepts of mathematics as they apply to the study of radio. Now, before I get started, you'll see on the menu up here I have exponents, notations, and some algebraic tips I wanted to give you. First, I wanted to say, if you're not a big fan of math, don't get too excited about this and don't get intimidated. Absorb what you can, enjoy what you can, and let everything else just go by you. When you get to DCL 093, I believe your eyes will open a bit and you'll think to yourself, wait a minute, some of that stuff in 092 is now more interesting to me. So you may end up coming back to this video later. Also, I hate to bring this up, but the allergies here in Texas are driving me out of my mind. So if I hesitate or mute the mic or whatever, again, I'm just trying not to cough in your ear. So in this episode, we'll do exponents, the various forms of notation, and again, I've got some algebraic hints or tips for you. This should provide you well, along with 091, for 093, where I kind of try to drag it all together, and hopefully you'll really understand a lot of concepts about radio, even if you're very new to radio. Let's start off with good old exponents. Any number raised to a power is that number times itself, power times. Now, I don't know about you, but that has to be the worst description of a mathematical process in history. I didn't write it either. I don't know if I can write it any better, so let's just look at what that really means. What we see here is a base 10 expression. 10 is going to be the base, 2 is the exponent. Now, what's happening here is the 2 means multiply 10 times itself 2 times. We also talk about the exponent being the power. I'm raising 10 to the power of 2 using an exponent of 2. So exponent and power are used kind of for the same thing. So don't let that confuse you. An exponent is also a power, and a power is an exponent. Now, a pattern emerges very quickly. What would 10 to the 1 power mean? Well, 10 to the 1 power just means 10. So what would 10 to the 0 power mean? Well, the explanation for this gets really complicated. I won't bore you with it, and I won't confuse myself with it. But 10 to the 0 is 1. In fact, any number raised to the 0 power is a 1. So starting off with this, what do you suppose happens if the exponent turns negative? You probably already noticed an interesting pattern of the decimal point moving over one space. Well, that pattern is going to continue. And this pattern, of course, does not stop. This becomes very powerful really quickly. And it's something you kind of might want to memorize or just work into your head if you don't want to take the time to do the math to figure out why the exponents going negative do that. And believe me, I haven't bothered with it. I'm busy enough with other things. Now, there's something you want to remember, and that is 10 to the 3rd power is, of course, 10 times 10 times 10. That's 1,000. 10 to the 6th power is a million, or mega. As you've probably guessed, these become very important in radio. We talk about kilo units and mega units quite often, like megahertz or kilohertz. So this does become important, although, frankly, I'm going to admit to you, you probably won't use it very often, if at all. But it's a powerful thing to remember. Now, exponents are part of scientific notation. How do you suppose you could express 6.28 megahertz? Well, really, it's the same thing as 6.28 times a million, or 6.28 times 10 to the 6th power hertz. If 10 to the 6th power means million, those two numbers I've got down below there express the same value. The value they express is 6,280,000 hertz. In fact, all three of these numbers now are all the same number expressed in a different way. When we express a number as a decimal number times 10 raised to a certain power, we are expressing it in scientific notation. Now, exponents and scientific notation can make math easier. You'll probably never have to do this, but there's a power here I wanted you to be familiar with, because it actually can help you later on if you're like trying to design or figure out a circuit. This kind of math becomes very powerful, especially if you don't have a calculator next to you, or you've got a calculator that rounds numbers off a lot. It messes you up. Here's a way to do math with very big and very small numbers and not have the rounding of the calculator inhibit you. What are these numbers really? What are we really looking at? 6.2 times 10 to the 6th power is 6.2 million. What's 2 times 10 to the negative 6? That's 2 millionths of something. Because even though these are two distinct numbers, because we've turned them into four numbers multiplying times one another, we can regroup. Now, keep in mind, it's 6.2 million times 2 millionths. Let's pretend we don't know that. Instead, let's regroup. Let's do this. Because 2 times 6.2 is easy. That's 14.4, right? Am I doing the math right? No, that's 12.4. 2 times 6.2 is 12.4. All right. So what's 10 to the 6th power? Well, it's a million. What's 10 to the negative 6? Well, it's a millionth. So we're really doing this math. But here's a cool little shortcut. 10 to the 6th minus, well, I should say 10 to the 6th combined with 10 to the negative 6 is 10 to 0 power. What is 10 to 0 power? Remember, 10 to the 0 power is 1. So the answer to our math problem is 12.4. What's even more powerful is if we were multiplying 6.2 times 10 to the 6 times 2 times 10 to the negative 24, you could take 6 minus 24, do the math, and realize that you actually are multiplying 12.4 times 10 to the negative, what would it be, 18th power, I believe. In any event, it makes math easier because you can just deal with multiples of zeros, and you don't actually need a calculator. Now again, as I said before, don't get all wrapped up in this. If it's boring to you, or if you just can't believe you're being drugged through this kind of math because you want to know something about radio, don't worry about it. Not that big of a deal. But kind of try to absorb what I've just said, because now we want to talk about scientific notation and how you might make your life easier using it. So what is scientific notation? Well, let's talk first about how to use it, and then you'll see what it really is. Here we have the speed of light, but let's just, for the sake of argument, let's round this to 300 million meters per second. If you wanted to express that in scientific notation, what you do is you take this 3 and you multiply it times a number that will equal 300 million. And that's how you would do it, because you've got to have 8 zeros after it. So you need 10 times 10, 8 times. So the speed of light is 3.0 times 10 to the 8th meters per second. I'm going to come back to this example in just a moment, but here's a better example. How would you tell someone what the weight of the Earth is? I know, and probably you know, that right here is the million mark. Here's the giga mark. One of these is a quadrillion, one's a trillion. I don't know which one's which. I have no clue how to say this number. So if I've got to explain this to someone, or if I read it in a book, how would I explain it to them? Well, there's a really cool way to do it with scientific notation that's very accurate, and you can communicate to someone else very easily. You would take this decimal point here and move it. I would move it to here. You could move it to here, but I would just move it to here. Now count the number of zeros after. So it'd be 13.17 times what? Well, there you go. If you counted from the decimal point, we've moved the decimal point here. So that means it's here. So there's 3, 6, 9, 12, 15, 18, 21, 24. Okay, so we've got to multiply it times 10, 24 times. Now I can tell someone, hey, I read in a book the weight of the Earth is 13.17 times 10 to the 24th pounds. Or I could say 1.317 times 10 to the 25th pounds. Or I could say, well, I probably wouldn't. I could say 131.7 pounds times 10 to the 23rd. In any event, this makes our life a little easier if we're going to describe a really big, or really little number. This is what we call scientific notation. Now, there's something called engineering notation. If you understand scientific notation, or if you understand engineering notation, scientific notation is easy. Remember back when I told you, I believe it was in 091, in radio and electronics and engineering, we only care about these designators. These 7 essentially are pretty much all we care about. So we want to express numbers in these values. Each of these values has a 10 power, of course, attached to it. So now, how would I express the speed of light in engineering notation? Because 10 to the 8th power, that's not one of my choices. I've got to use one of these other choices. Well, the easy one, I'm sure you'll agree, is we call this 300 million meters per second. So why can't we express it in millions? So it would be 300 times a million meters per second. And a million is 10 to the 6th power. So this is scientific notation. This would be engineering notation. Now you might be asking, well, could you use that 10 to the 9th power? Technically, that is the speed of light in engineering notation, except there's a little secret rule that everyone pretty much obeys, and that is that in all cases of scientific or engineering notation, the number has to be greater than 1. Preferably, it's less than 10, so you keep the decimal point right here. But in engineering notation, it can be greater than 10, as you can see right here. That's the line between scientific notation and engineering notation. If you look in physics textbooks talking about engineering matters, most of the time, results of a calculation will be an engineering notation. So that means when the number is expressed, this here will be one of these almost all the time. Now, as you are building the equation and putting in your variables, you might use scientific notation. But when you get an answer, they're usually going to express it in engineering notation. So again, that's engineering notation. Once you understand scientific, engineering is, as I said, very easy. I want to spend a few minutes not doing any math, but showing you some things about formulas. I want to show you how to use a formula to learn about a circuit or learn about how it operates without doing any math. Let's start with good old Ohm's law. Hopefully you're familiar with this, but if not, E is in voltage, that's the electromotive force that drives everything. R is the resistance in ohms, and I is the current in amps. The way we use this is, let's say we wanted to find current. We'd put our thumb over current. That leaves me with the E over the R. What is an E over an R? An E over an R is a division problem. Of course, there are other letters here. You can put your thumb over. If I don't know my resistance, I can use my voltage divided by my current and calculate my resistance. Let's stick with this one. Can this tell me about the circuit without doing any math? It actually can. If I had 12 volts and there was 12 ohms in the circuit, I'd have 1 amp of current. If I doubled the voltage, in other words, I'm going to double the E, it's obvious what happens. My current doubles. So now we've learned the first thing, and that is whatever's on top in the formula, when it goes higher, the output goes higher. What happens if what's on the bottom goes higher? The output goes lower. So if what's on the bottom goes higher, this goes lower. If this goes higher, this goes higher. That applies to any formula you look at. What about this weird one? This is a formula for power. You put in the voltage on top, you put the resistance on the bottom, and you get the power in watts out of the equation. So let's try 3 volts across 9 ohms. Now, if I increase the voltage on top, the power goes up. You saw before, if I increased the voltage, if I doubled it, my output went up by double. What happens if I double my voltage to 6 volts? The output does not double. It doubles twice. It goes to 2, then it goes to 4. That is, of course, because the voltage counts twice. So its effect is amplified. That brings us to another rule. If you see a squared value, or cubed or more, cubed would be if this was a 3 up here. If you see this raised to any power, whatever that letter is becomes much more powerful and much more influential. Just looking at this formula, which is a formula used to calculate the inductance of a solenoid, now you know, well, let's see, we're trying to find the inductance, which is L in henries. Okay, so we're trying to find its inductance of this coil. The permeability of the coil is basically a measurement of how well the coil's core conducts magnetic lines of force. So we'll look this up in a book somewhere for whatever core we're using. We can already tell that if we increase the number of turns, the inductance goes up very fast. If we increase the area of the turns, the inductance also goes up, but not as fast as if we add turns. And of course, if we increase the length of the coil, the inductance is going to go down. Now, here's something we can learn. If I increase the number of turns, that's going to increase the length of the coil. But I can add a lot of turns in a very short distance. Plus, the turns count twice. So adding turns, even if the coil gets a little longer, will still increase my inductance. But look at it another way. You've got the perfect coil all built, but its inductance is just a little bit too high. What is an easy way of lowering the inductance just slightly? Well, if you increase the length, that would work. But you don't want to add turns. So what you do is you stretch the coil out slightly so the turns are a little farther apart. You have the same number of turns, you have the same everything, except slightly longer coil. That would lower your inductance slightly. The point here is to be able to look at a formula and get some general idea of how things work without doing math. You can't just do math every time you look at a formula. That gets tedious. But if you can look at a formula and get an idea what's going on, the formula can help you without picking up a calculator. Here's one more formula for you. This one is the formula to calculate the tuned frequency of an inductor and capacitor. In other words, a tuned circuit. So if you want to design a receiver or a transmitter or a power amplifier or whatever, and you want to tune it to a certain frequency, you've got to know how much inductance in the coil and capacitance in the capacitor you need. Now, the first thing you'll notice is these numbers on bottom are under a radical sign. That's the opposite of raising something to a power. So when these numbers change, their effect is a lot slower. It still happens. So we know if we increase this number on the bottom, the frequency goes down. If we make this number smaller, the frequency goes up. We also know that 2 never changes, the value of pi never changes, so the only thing that changes the resonant frequency of the circuit is the value of the inductor and capacitor. So we're going to make them smaller and smaller to get this frequency to go higher and higher. But the change is somewhat slow because you're taking the square root of their product, which again, that's the opposite of raising that value to a power. So let's try something here. Here's your variables. We're looking for the frequency. We use inductance and capacitance to calculate it. Let's say I want my frequency that it tunes to be 1 megahertz. That means the number down here, this number has to equal 0.000001. Problem is, whatever number I have as a square root here is multiplied by 2 times pi, which is 6.28. So this number has to be super, super small for the result to be this. In fact, it has to be really small. To get the bottom to be this number, I take 6.28 times this number. And here's a good example why I used scientific notation. The number is so small, I'd barely have enough room on the screen to display all the digits. So I went with this. The point here is to be able to look at a formula, not do any math, and have a general idea what that formula is telling you about the circuit. If you have to, go ahead and do math. But my point is, it's a powerful tool to be able to look at a formula and get information out of it without doing math. And of course, don't forget the rules. Anything on top getting bigger makes a bigger output. When what's on the bottom gets bigger, you get a lower output. That is so fundamental to any formula. I hope that in time you grasp how important this little concept on the screen is. And many of you are very familiar with math. This is nothing new to you. I am talking to those very new to radio who never got into math, never liked math, and quite frankly still don't like math. I hope this has been helpful. The next episode, 093, I'm going to use the contents of 091 and this video to show you several new things. I'm promising one more time to try to keep things very understandable. I realize I'm probably, for some of you, leaving some things out that frustrate you. Well, the idea here is to make this fit and be useful to those that are very new to radio and, again, are not really into math. Once we get past DCL 093, most of my videos on this channel don't really do a whole lot of math. You don't deal with math a lot with my stuff because I'm trying to teach basics. Everything on my page will always be basics. If you want to learn a lot about radio and engineering, you're going to have to move on from me rather quickly. Again, thanks for watching, and I'll see you next time.